Okay, block on block part 2. If you haven't done part 1, go back and do it now. This is a harder problem. In part 1, we had a mu of 0.1 between the two blocks, and now in part 2, we're going to add a mu. Okay? We're going to say, what if the mu here equals 0.2? So now there's going to be a coefficient of friction and a force of friction between the bottom block and the ground, which makes sense, really. So, how does that change our problem? What is the question? Well, the first question is, again, what is the maximum applied force that can be applied to the bottom before it slips? In part 1, we worked out that the maximum acceleration of the whole system couldn't exceed 0.98, or else the top block would slip, and nothing has changed in that situation, so we don't have to do that math again. The mu between 2 and 5 was all that we worried about, so it's all good. This is still going to be true. But obviously our answer to A for part 1 can't be our answer to A for part 2, so we got to redo the last bit. Now if we look at the whole thing as 1, it has a mass of 7, it's got a force of gravity, which is 7 Gs. There's also going to be a force of friction here. And that force of friction is like that. X is to the right. So in the x direction, our equation would say Fa minus Fx equals Fa. And the applied force would be equal to 7 times 0.98 plus, I said F, not Fx, plus Ff, which is mu Fn. But the mu is this mu Fn. So the y direction equation I'm going to need now to find Fn. I'm not going to assume they're equal, though of course it's going to turn out that they are. Fn minus Fg, those are the only two forces in the y direction. Good, so Fn equals 7 Gs. So therefore the applied force equals 7 times 0.98 plus 0.2 times 7 Gs. And the applied force here is going to work out to be about 21 newtons, 20.58 newtons. So that's not really very challenging. It was pretty much the same as part A. This is really the hardest part. And now that there's friction, it slows down a little bit. But part B is where it gets more interesting. Part 2B. Okay, so what is the acceleration of A if we apply 30 Newton force? So 30 Newtons, what's the acceleration of the bottom 5 kilogram block now? So we've got to draw another free body diagram of the 5 kilogram object. Is there gravity? Yes, of course. Is there a normal force? Yes. We don't need to worry about this again. Is this guy pushing down on it with a force of 2 Gs? Yes, it is. So there's this other force here. I'm just going to call it 2 Gs. I don't want to call it Fn2 and Fn5 or Fn1. And it's just too confusing. So it's 2 Gs. It's this force, Newton's third law. Again, you watched part 1. You know what I'm talking about. If you didn't, go back and watch part 1. Okay, so just like part 1, the applied force is to the right on 5. 30 newtons. And still there's this force, the force of friction from this guy, which I believe we said last time was equal to 1.96, right? When we did the math here, 1.96. So there's that force of friction acting on this guy, Ff, 1.96. But there's also another force of friction because now there's a mu between the surface and the 5 kilogram object. So the question is, what's that going to be equal to? And that's, of course, going to be mu Fn. So I better stop for a second and do my y direction equation. I'll do it up here. And my y equation says that Fn minus Fg minus 2g equals 0. So the normal force on this guy is equal to 7g. So that makes sense, right? The normal force has to be big enough to stop the 5 kilogram object from falling through the floor and the 2 kilogram object. So hopefully that makes sense. The normal force here is bigger than gravity. It's as big as gravity on both of them put together. Well, that certainly is logical. Okay, no problem. So then my force of friction over here is going to be 0.2 times 7g. Hey, that's the force of friction we just had over here. So now there's 2 forces of friction on the 5 kilogram object. So when I do my x direction equation, I'm going to say Fa minus 1 force of friction, which I'm just going to call 1.96, minus the other force of friction, which I'll call 0.2 times 7g. And that's going to equal Fa. Is that in the frame? Just barely. Rearranging that, I'll get that the acceleration equals 30 minus 1.96 minus, what did we say, 7g times 2, 13.72. All divided by the mass of this object, which is 5, and hopefully that turns out to be 2.864 meters per second squared, which of course I would round to 2.9. It looks like you can't see that at all. So I'll write it up here, 2.9 meters per second squared, which I can see.